We're going to look at this technique of partial fractions, how we decompose a fraction into its pieces. So it's sort of like the reverse of algebraic fraction questions. Normally we have a couple of algebraic fractions added together and we'd pull it all into one fraction. Well, this is going back the other way. So that's what we're looking for there. We have got a fraction and we want to decompose it into its pieces. First thing to do, if that degree of the numerator is more than or equal to the degree of the divisor, first thing I'm going to do is just a polynomial division. So I'll do that. That should leave me with a fraction where the degree of the numerator is less than the degree of the divisor. So then I'll go and factorise the denominator. Now, for each of those factors, I'm going to create the fraction that it came from. So if I've got a factor of x minus a, I need a fraction where the denominator was x minus a, and that means the numerator must be a constant, because if the bottom is linear, it's got to be of order 1 less. If I've got something like this, where I've got x minus a to the power of something, then I write a fraction for each of the powers going up to the top one. So if I had x minus a cubed, I'd have 1 for x minus a, 1 for x minus a squared, and 1 for x minus a cubed. The only other possibility for a factor would be a quadratic, because every polynomial, remember, can be factorised down to be a combination of linear and quadratics. So if it does turn out to be a quadratic, then in the numerator I'd need a linear function, 1 less in order, so ax plus b. Let's do, well, start with a simple one here. X squared on x plus 1. I can do a polynomial division on that. Let's actually do the division there. So x plus 1 into x squared would end up, there he is, we've done our division, and we get x minus 1 plus 1 on x plus 1. I can now integrate that. So here we go. We've got one where, well, there's no polynomial division to be done on this one. Let's factorise the denominator, which has got a common factor of x. That means I want to break it into 2 fractions. I'll have one where the denominator is x, one where the denominator is x minus 1. I've got to find a and b. If I multiply out by that common denominator, I get this equation to solve. There's different ways of approaching it. Sensible substitution is a good way, because if you pick your x carefully, you can get rid of one of the things you're trying to find here. If I make x equals 0, well then b goes away, and then I've got a straight away. Well, a is negative 3. And then the next number to substitute in would be x equals 1, because now the a will go away and I get b equals 3. Another way you could approach it is to compare the coefficients on each side using that identity idea. So the constant must equal the constant. There's no constant with the b's, but negative a therefore must equal 3. If I look at the coefficient of x, I'd have a plus b then is equal to 0. I've just found out that a is negative 3, so b would be 3. I've got it into its 2 fractions. They're both log functions. When I notice the coefficient of the log is basically the same number, I'm not worried about the sign, then I'm going to use my log laws and pull that into one nice log, 3 log x minus 1 over x. Quadratic on the bottom, let's factorise it. So this time I'll let x equals negative 2, I get b is negative 3/7, and now I'll make the b disappear, so x equals 5, I get a as 10/7. I have my 2 fractions, again we turn out to be log function. You're going to see a lot of log functions if you think about it, because if the denominator is linear and I've got a constant on top, it's got to be a log. In this case I didn't bother recombining them because the coefficients weren't the same. I mean, I could make them the same. I could bring the 10 into that one and make it x minus 5 to the power of 10. The next one I could bring the 3 in and make it x plus 2 to the power of 3. Then they've both got a coefficient of 1/7. What will we get? 1/7 log of x minus 5 to the power of 10 over x plus 2 cubed. Couldn't be bothered. Alright, let's have a look at this one. This time we've ended up with a quadratic as one of the factors. X squared plus 1 doesn't factorise down. If here we go, I've got a factor of x over here in this second one. If I make x equals 0, that'll make both the b and the c disappear. A equals 1. Now I'm going to make the a disappear. And so yeah, of course you can use complex numbers, there's no reason why not, they are numbers. Now I can look at this and say, well, the real part must equal the real part, the imaginary part must equal the imaginary part, therefore b equals negative 1. C equals 0. The first one again is a log function. What's the second one? Well, actually that's going to be a log function too, because the derivative of x squared is 2x, So I've ended up with a couple of logs once again. I didn't bother with the absolute value on the second log because of course x squared plus 1 is always positive, but again if you put them there it doesn't matter. Ooh, this one's been factorised for us already, but we've got a multiple root there, x plus 1 squared. So I'll need two fractions, one for the x plus 1 in the denominator, one for the x plus squared in the denominator. Okay, what's going to be a smart thing to substitute in here? If I make -1, that means the first goes away because that, and also that last one goes away as well because the x plus 1 squared. I get left with b is -1/2. Again, if I use x equals I can work out c and d now. That still leaves me with a to find. I'll just pick a number. I can't think of another number that's going to make everything cancel to leave me with just a. So if I just substitute in 0, it's an easy number to substitute in. I get 2a plus b plus d is 0, but I've worked out b and d, so I can get a. And you could say all that work for nothing. Okay, there's what we have to integrate. Oh, we haven't got log functions this time. So because we've got x plus 1 squared there, that's going to be 1 on x plus 1, and the other one is an inverse tan function. But there is another way of finding those constant values known as the cover-up method. It can be a lot quicker. So if you've got something like this, you've decomposed it into its different factors, then to work out a, what you do is you substitute a into the fraction, but ignoring the factor that would create 0. Because you can't have 0 on the bottom of the fraction. The reason it's called cover up, it's like saying, oh, well, let's just cover it up. We'll pretend it's not there and we'll substitute into that. That'll work out a. And then if I wanted to work out b, I could do the same thing. I'll substitute in, but ignoring the x minus b one. That would be 0. That's no good. We get b, and so on for all the different ones. That's the idea. Well, let's go back to the examples we did earlier. So now, looking at this one, all I've got to do is, well, a, okay, I'll substitute it into the fraction. The x, as far as I'm concerned, is not there. So it's 3 on 0 minus 1, it's -3. And to work out the b, well, I'll cover up the x minus 1, and we get 3 on 1, it's equal to 3. So you're substituting in what would make that equal to 0. So this one here, that was our next example. If I want to work out the a, I'll sub in x equals 5. The x minus 5 is not there. We get 5 plus 5 on 5 plus 2. There's the 10 on 7. And the b, substitute in -2, we get -3/7. So it works really quick when you've got linear denominators. And a lot of people say that the cover-up method is just for that, but no. You can still use that idea for quadratic ones as well. We had this one, if I use the cover-up. All right, a, cover it up, sub in 0. But again, the idea simply is, what would make the factor equal to 0? Again, let's use complex numbers. If I cover up, then on the left-hand side now I've got bi plus c, because that's what we're trying to find. And on the right-hand side, it's just 1 over I. The reciprocal of I is -I. Real part equals the real part, imaginary part equals the imaginary part. So we can still use complex numbers to help us to do the quadratic ones. This one then, okay, that linear one, always going to be straightforward. The next one, what would make 4x squared plus 1 equal to 0? Well, that's a half I, or I on 2. Well, you get there. A bit of work. So sometimes it might be better to use a combination of ideas. The linear one, always cover-up's going to get you real quick. The quadratic one, I guess it just depends whether the substitution is going to be nice or not, whether you want to do it that way. What about the multiple factor questions? Now this one, okay, the A, again, easy to work out. But what happens with the B? Because I've got two fractions here that when I substitute in one, I'll get 0. So will I be finding B, or will I be finding C, or will I be finding B plus C? And the answer is you'd be finding C, because if you look on the right-hand side, that's the factor you've got there. So that's the fraction it will find. So the higher power will always be the one. All right, in that case, substitute in C for the x minus 1 squared one. I get 9 on 2. Right, C is 3. I've got 3. I don't have B though, and I can't really use the cover-up method to do it. I'll just do a simple substitution. Well, 0 is an easy number to work with. If I substitute it in, I haven't bothered expanding the whole thing out, and I just subbed it straight in. We know what A and C is, we can work out B. All right, let's try this one then. Well, B, I'll work out straight away. That's got the linear one, but it's the x plus 1 squared I'm going to be finding using the cover-up method because it's the highest power. Okay, now for the CX plus D. Okay, cover that one up, substitute in I. I'll have Ci plus D is I on I plus 1 squared. I plus 1 squared is 2I. I's cancel, that's a half. Real part equals the real part. Imaginary part equals the imaginary part. Now I've got to find A. I'll just let x equal 0. Get a simple number to sub in. I'll end up with A plus B plus D is 0. We know what B and D are, and we get A is 0. Well, what happens if that quadratic denominator can't be factorised? There's something like this. I mean, x squared plus 4x plus 5 can't be factorised. But yes, it can. Remember, all quadratics can now be factorised because we know about complex numbers. Let's find A first of all. It's the linear one. That's going to be easy. So, bang, we've got that. Complete the square if you don't see it straight away. Okay, I'll go x plus 2 squared plus I. So in other words, I'm going to substitute in minus 2 plus I. That's what that would make that equal to 0. So let's substitute it in. That's what we've got to resolve. Okay, realise the denominator. Eventually we get there. Imaginary part equals the imaginary part, then the real part equals the real part. Again, it's an example of, is that amount of working worth our time, or would just a simple substitution have been easier? It's about having multiple ideas to play with. You just use what's going to be best for the question that you got. 4D, this idea of partial fractions.